I have to admit, when I first saw the source material for today's deep dive, I almost just put it back on the virtual shelf.
Oh, yeah.
I saw Schrödinger's cat in the title, and I immediately thought, okay, we've done this.
Yep.
Everyone has done this. It is the stairway to heaven of physics examples.
It absolutely is. It's the single most famous trope in pop science. I think I've seen it in everything from serious textbooks to, I don't know, sitcoms. It's unavoidable.
Exactly.
Yeah.
You know the drill, right?
Yeah.
There's a box, a cat, some poison, and until you look, the cat is a ghost.
Yeah.
We get it.
We get it.
But then I actually opened the manuscript,
Oh.
and I realized why you put this in the stack. This isn't just another philosopher waxing poetic about the nature of reality.
Yeah, not at all.
This is a paper by Reza Rezi Khan titled Probing Schrödinger's Cat with Neutron and Cosmic Radiation.
Mm.
And the reason we're talking about it today is because of one specific massive claim. The author isn't just talking to the cat. He's proposing a blueprint to actually test the paradox.
That is the hook. I mean, usually this whole topic is purely abstract. It's a debate club question. But this paper is effectively an engineering proposal. It's asking, can we build a machine that looks inside the box without opening the box?
Without collapsing the wave function.
Can we measure the cat's state without collapsing the wave function? Yes.
Which, if I remember my Physics 101 correctly, is supposed to be the one thing you absolutely cannot do. The golden rule of quantum mechanics is basically, you touch it, you break it.
That is the central dogma, yes. The moment you measure a quantum system, you force it to choose a state. You destroy the magic.
Right.
But Kankha is arguing that we can use something called phase-encoded scattering to essentially cheat the system to get the information without paying the price of collapse.
That is a bold claim. So our mission today is to figure out if this is actually genius or just, wishful thinking.
Mm-hmm.
We need to understand how you can possibly see something without light, what phase-encoded scattering actually means in plain English, and why this might change how we understand the universe.
And to do that, we do have to briefly set the stage with the original experiment. But I promise we won't linger on the pop culture version. We need to look at the mechanics, because the flaw in the original setup is exactly what this new paper is trying to exploit.
Fair enough. Okay, let's go back to 1935.
Mm-hmm.
Erwin Schrödinger is arguing with Einstein, trying to show that quantum mechanics has some absurd implications. So he invents this scenario.
Right. He creates a Rube Goldberg machine of death. You have a sealed steel chamber. Inside, you have the cat.
And the radioactive material.
You also have a tiny sample of radioactive material. It's so small that there's a 50-50 chance a single atom decays within the hour.
And this is the bridge, right? This is where the micro world, the quantum world, shakes hands with our macro world.
Exactly. If the atom decays, which is a pure quantum event, a Geiger counter detects it. That detector triggers a relay, which releases a hammer, which shatters a flask of prussic acid poison, kills the cat.
It's grim, but effective.
Very effective. The logic follows that because the atom is in a superposition of decayed and not decayed until we measure it, the math dictates that the cat, which is entangled with the atom, has to enter a superposition of dead and alive.
Okay, and this is where the source material brings up a really interesting nuance that I'd never really considered before. The paper spends a good amount of time distinguishing between a dead cat and an asleep cat.
I loved this part. It seems like such a pedantic little detail, but it's physically crucial. Tangha points out that people often confuse asleep with some sort of dormant or, off state.
But biologically, it's not.
Not at all. Biologically and physically, an asleep cat is 100% alive. It's breathing, its blood is pumping, its neurons are firing.
It's definitely not dead.
Definitely not.
Yeah.
So in the quantum math, asleep and awake are just subfolders in the alive directory. They are classical variants, but dead is orthogonal. It's a completely different state of matter.
And that leads to the second point the paper makes, which is really the foundation for the whole new experiment. What actually happens to the atoms when the cat dies?
This is the thermodynamics part.
Right. Because I think people imagine that in the dead state, the cat just becomes an object. But all the atoms are still there.
Yes. They don't vanish. When the cat dies, the carbon, hydrogen, oxygen atoms are all still inside the box. But the entropy changes. Life is a low entropy state. It's a highly organized structure fighting against chaos. Death is a rapid transition to high entropy, disorder.
So the alive state has a specific shape, a specific energy configuration, and the dead state has a completely different one.
Correct. The mass distribution changes, the
Hmm.
potential energy field inside that box changes. The information isn't erased, it's just redistributed. And that difference in how the mass and energy are arranged, that's what this new proposal wants to exploit.
So we aren't looking for a ghost. We're looking for a difference in density.
Precisely, a different physical landscape.
Okay, hold that thought, because that is the key. But before we get to probing this poor cat with neutrons, I think we have to address the cat in the room. Why is this even still a debate? We've had quantum mechanics for a century. Why can't physicists agree on what happens in the box?
It's the measurement problem. We have the math, the Schrödinger equation, and it works perfectly. I mean, it predicts lasers, transistors, everything we rely on. But we don't agree on what the math represents in reality.
Let's run through the interpretations just to see the landscape. It's like a political spectrum of physics. You've got the establishment view, the Copenhagen interpretation.
Or in Heisenberg. This is the standard textbook view. It says the superposition is real, but the moment you open the box, the moment of measurement, the wave function collapses. It instantly picks one state.
I always found this one so frustrating. It feels like a video game that only renders the room when you open the door. It doesn't explain how the collapse happens.
It just says it happens.
It just happens.
Exactly. It creates this awkward boundary between the observer and the observed. So to get rid of that special collapse event, you get the many worlds interpretation.
Ah, the sci-fi favorite. No collapse, just splitting.
Right. In MWI, the universe just splits. In one branch, the atom decayed, cat's dead. In another branch, the atom didn't, cat's alive. And you, the observer, you split too.
Which solves the math problem, but creates a pretty big storage problem. Where are we keeping all these infinite universes?
That is the standard critique, yeah. Then you have more cynical takes like quantum Bayesianism or cubism. This one is more psychological. It says the wave function isn't a description of the world, it's a description of your beliefs about the world.
So when I open the box, I'm not changing the cat. I'm just updating my own betting odds.
That's it. It solves the paradox by saying there is no physical paradox, just a lack of information.
But the paper also mentions pilot wave, or Bohmian mechanics. This one fascinates me because it suggests the cat was always definitely dead or alive.
Yes, pilot wave is deterministic. It says there's a real particle and a real wave guiding it. The cat has a definite state the whole time, but this guide wave is doing all the quantum dancing in the background. We just couldn't see it.
And finally, decoherence theory, which feels like the most practical one.
It's very popular experimentally. It says the environment, air, molecules, photons, heat, is constantly bumping into the cat. These tiny interactions suppress the quantum weirdness and make it look classical very, very quickly.
So the air in the box is kind of measuring the cat all the time.
Precisely. But even with decoherence, we're still stuck inferring what happened. We assume the superposition was there and got destroyed. Kangha's paper is asking, can we verify the superposition implies reality while it is still happening?
Can we see the cat in the middle of being both?
Can we see it? Yes.
Okay, the pivot. Let's get to the experiment. The paper starts by shooting down the most obvious idea. Why not just shine a light in the box?
The photoelectric effect.
Right.
Shine a light, photons bounce off the cat. If the cat is alive and standing, the reflection comes from one height. If it's dead and lying down, it comes from another. Simple.
But the paper says this is a hard measurement.
A photon hitting an electron is a violent event in the quantum world. It transfers energy. It's a kick. And that kick is more than enough to collapse the wave function. You've tainted the sample. You've opened the box without opening the lid.
So light is too heavy-handed. And this brings us to the hero of our story, the neutron. The paper proposes neutron interferometry.
This is the core innovation. Instead of light, the author says, let's use a beam of very low-energy neutrons.
When neutrons, what makes them the perfect spy?
Two things. One, they're neutral. No electric charge, so they pretty much ignore the electron clouds that stop light. They can pass right through the steel box and the cat without getting absorbed easily.
And two,
they interact via the strong nuclear force and gravity, but only at very short ranges, so they're weakly interacting in this context.
so instead of bouncing off the cat like a tennis ball, they just ghost through it.
It goes through, but, and this is the crucial insight, they don't go through unchanged. The matter inside the box, the cat, creates a potential landscape.
Okay.
Think of it like walking through a room filled with water versus a room filled with air. You can move through both, but the resistance you feel is different.
I like that. So the neutron wave passes through the box. If the cat is alive, standing up, low entropy, the neutron wave experiences one kind of landscape. If the cat is dead collapsed, high entropy, It experiences a totally different landscape.
And that difference imparts a phase shift.
We need to define this clearly for everyone. What is a phase shift in this context?
Imagine the neutron is a wave, like a ripple on a pond. As it passes through the alive cat potential, the peaks and valleys of that ripple get shifted forward or backward slightly. Let's call that shift phi.
Okay.
If it passes through the dead cat potential, the shift is different. We'll call that phi.
So the neutron comes out the other side, carrying a kind of timestamp. I was delayed by an alive cat, or I was delayed by a dead cat.
Exactly. But remember, the cat is in a superposition. It's both alive and dead at the same time.
Right.
So the neutron interacts with both potentials simultaneously.
My brain hurts. So the neutron wave itself splits.
Effectively, the neutron leaves the box in its own superposition of phases. It has the alive shift and the dead shift encoded onto it at the same time.
And this leads us to the math. There's a specific formula in the paper that I want to look at. It describes the probability of detecting the neutron at a certain angle. It goes something like P of beta equals alpha squared FA squared plus beta squared FD squared. And then there's this cosine term.
Let's break that down. The first part is pretty standard. Probability of detecting a neutron if the cat is alive, plus the probability if the cat is dead. If the system were classical, that's all you would have, two blobs of probability added together.
But it's that third term, the interference term. That's the one.
Yes. The part that goes 2 alpha beta times FA times FD times cosine of delta phi. That cosine term, that is the smoking gun.
Why is that the smoking gun?
Because that term represents interference. If the cat were definitely dead or definitely alive, that term would be 0. It wouldn't exist. But because the cat is both, the alive wave and the dead wave of the neutron interact with each other.
Like noise-canceling headphones.
Exactly like that. In some places, the waves add up to a strong signal. In others, they cancel each other out to 0. That creates a fringe pattern. Stripes of neutrons and no neutrons in the detector.
So if we put detectors outside the box and we see stripes, an interference pattern, we know for a fact the cat is still in a superposition.
Yes, we have proven the cat is both dead and alive without ever forcing it to choose. We've seen the shadow of the superposition.
And if we don't see stripes, if the pattern just washes out into a blur,
then we know the system has collapsed. Maybe the box leaked heat, maybe the cat was just too massive and gravity collapsed it. But the interference pattern is the signature of quantum coherence.
that is incredibly clever. It turns a philosophical paradox into a signal processing problem.
It really does. It treats measurement not as a hammer that smashes reality, but as information extraction. It's what we call a weak measurement. You extract just enough info to know the superposition exists, but not enough to figure out which classical state it's in.
The paper takes us a step further, though, and this is where things get a little cosmic. Conga suggests we don't even need our own neutron beam generator. We could use the universe itself.
The cosmic connection. I found this part fascinating. The paper suggests using cosmic microwave background photons, or even better, cosmic neutrinos.
These are particles that have been traveling since the Big Bang, just passing through everything.
Right. Neutrinos, specifically, are passing through your body, my body, and Schrödinger's box by the trillions every single second. The paper argues that these cosmic particles act as natural probes.
So theoretically, if we had detectors that were sensitive enough, we wouldn't need to build the experiment. We could just analyze the cosmic neutrinos coming out of the box.
In principle, yes. The universe is constantly performing this experiment on everything. These particles are picking up tiny phase shifts from every object they pass through. It links the quantum state of the cat to the cosmological background of the entire universe.
I have to ask the practical question. We aren't actually going to put Fluffy in a box and radiate her with neutrons, are we? Please tell me this is theoretical.
No animals were harmed in the making of this hypothesis. When physicists talk about Schrödinger's cat in 2026, they usually mean cat states. These are experimental analogs.
Like what?
Superconducting qubits, trapped ions, or optomechanical resonators. Basically, we take a macroscopic object, like a tiny vibrating mirror or a loop of superconducting wire, and we put it into a superposition of two distinct states, vibrating and not vibrating, current flowing left and current flowing right.
So we would fire neutrons at a tiny vibrating mirror.
Exactly, to see if we can detect if it's vibrating and not vibrating simultaneously without actually stopping the vibration.
Okay, so we have the mechanism. We have the math. What's the payoff? If this works, if Kunka's right, does it actually solve the measurement problem?
It doesn't solve it in the sense that everyone will suddenly agree and go home. But it would be a massive point in favor of the idea that measurement is a physical, information theoretic process, not some mystical event.
It removes the need for a conscious observer.
Completely. The neutron doesn't have a consciousness, it doesn't have a PhD, but it can measure the system. It suggests that the boundary between the quantum world, where things are magic, and the classical world, where things are normal, isn't a hard wall, it's a gradient.
A gradient of information.
Right. The more information leaks out via neutrons, air molecules, thermal radiation, the more classical the object becomes. Conca's proposal gives us a way to watch that leakage happen in real time.
It makes me think about the privacy of our own reality. If this is true, is anything ever truly isolated?
That's the deep question. The paper touches on this. If cosmic neutrinos are constantly streaming through the entire Earth, interacting weakly with every single atom.
Then they're constantly carrying away phase information about us, about everything.
Exactly. They are encoding the state of every person, every rock, every cat into their wave functions and carrying that information off into deep space.
Which brings me to the provocative thought I wanted to end on. If the universe is full of these natural probes, if the cosmos is constantly looking at us with neutrinos and CMB photons,
Then the universe is effectively measuring itself constantly.
does a true superposition ever really exist? Or are we all being collapsed into reality every nanosecond by the faint light of the Big Bang?
It suggests that splendid isolation, the whole idea that you can truly separate a system from the rest of the universe, that might be the biggest fiction in physics. We are all entangled with the cosmic background.
So we are all Schrödinger's cats, but the lid was blown off the box 13.8 billion years ago.
That is a beautiful, if slightly terrifying, way to put it.
On that existential note, we're going to wrap up this deep dive. I want to thank you for walking us through the phase shifts in the math. It turns out you can teach an old paradox new tricks.
It's always a pleasure. Keep your wave functions coherent, everyone.
Thanks for listening. We'll catch you in the next deep dive.